slowly to the cloud. Understand? Hasn't been the same for the logic, but
Usually this happens,
I was thinking.
but usually they're not like giving up. They just stop showing up to lecture and then start falling behind and then they give up. But it's a little bit concerning that they're gone right now, but not concerning yet. Yeah. All right. So we are going to start finite state machines. So you guys did your reading on finite state machines. So you can see that we are now able to do and make some real systems, some implementations that will do a function that we desire with finite state machines. All right, so here is our circuit for a finite state machine. We are going to use combinational logic, which we know consists of truth tables, our Boolean equations, and then we have the logic diagrams. And we're also going to use sequential logic, and this is going to store our state and excitation tables. And we're going to be using flip-flops in order to store our states. So if we look at a RTL level description, it would look like this. We have some registers that is going to store our state information. And then we have some combinational logic that's going to take our inputs and our current states and update us on what the next state should be. And 1 second. And also based on the current inputs, the current states, we have an output that changes, right? So here is a small example of a finite state machine. Here we're just counting with 2 bits, so 0, 1, 2, and 3. And we have to give our states a binary value in order to know what state we're in. And usually the convention is if I'm labeling a state as S0, I'm going to give it the binary pattern representing 0, right? So in that case, if we want to fill this table, I'm in 0, 0. What is my next state? It would be S1. So I would again give S1 the encoding that represents binary 1, right? So Q of 1, we would want it to change from 0, 0 to 0, 1. Okay, that would be going from 0 to 1. And then if we are in state 1, we want to go to 2. If we are in state 2, we want to go to 3. If we are in 3, we go back to 0. Right? So this is a very simple example because we don't have an input. We're just always counting, right? On the next cycle, I'm going from 0 to 1. If I'm in 1, I'm always going to 2. If I'm in 2, I'm always going to 3. If I'm in 3, I'm always going to 0. So this one would just count from 0 to 4, repeating, right? And if we were going to create this into a circuit, what do we think it would look like? You can answer this one on your own first. You have a code today. It is 584. Hey, I don't see any answers changing anymore. Is anyone still thinking about this? All right, so we are not quite at the threshold. We do like two popular answers that are close to the answer. So talk to the people around you. Let's see if we can get more people picking the right one.
Okay, so wait. This is one.
I hear diverging discussion, so let me just check to see how much we moved. We moved a little bit. All right. So I mentioned you guys have two answers that are close, right? So the two answers that are close are B and C, right? So the question is, which one is right, B or C? So which one do we like? Do we have a reason?
B.
All right, so you like B. Why do we like B?
Because you know the previous state of both bits.
Yes. You need to know both bits, right? A D flip-flop holds how many values? 1 bit. I have how many bits to encode my state? 2. Right? So I need to remember 2 binary values to know what my current state is, so I can then evaluate that to calculate the next state. So I need 2 D flip-flops in this case. So if I had 3 state bits, how many flip-flops would I need? 3, right? And then how about if I needed 5 states, how many flip-flops would I need? So how many bits do I need to represent 5 different patterns? 3, right? 2 is not enough. 3 is more than enough, right? But it's the minimum. So then I would, if I had 5 states, I would still need 3 bits. All right. So we store the current state using the D flip-flops so that the inputs to the combinational circuit don't change while the output is computed, right? We talked about that, why we use flip-flops. And then the transition to the next state only occurs at the rising edge of the clock. And if we implemented the combinational logic part of the circuit, it would look like this one. So this is Q0, this is Q1, right? Q0 the lower bit changes every single time. So that's why it's just connected to an inverter. And then Q1 will change pretty much every other time. Which is why it works with the XOR gate. But you could just figure out that the XOR gates works by looking here. What is this? Yeah, it's the XOR gate, but more importantly, what does it look like? From combinational logic? What kind?
An encoder.
More way back. A table that shows based on the inputs, what is the outputs? This is just a truth table, right? It has multiple outputs, but you can just look at them individually. Like if I wanted to figure out what's the combinational logic to implement in order to update Q1, I just make a truth table like this. And then if I drew out the K-map, I would circle these together, right? And I would find that, well, actually they would be individual circles, but I would find that I can implement it with an XOR gate, which is just A and B naught or B and A naught, right? And then you could do the same thing for Q of 0, right? So here is our definition of finite state machines. So they are going to consist of a set of states, a set of inputs, as well as a set of outputs. You need to have an initial state. The initial state is indicated by an arrow coming out of nowhere with no inputs on it. And then there is a set of transitions. So only one transition can be true at a time. It's going to be based on what is my input, what is state that I'm currently in. So like here, I'm going from the initial state to state A if my input is A. If my input is B, I go to B. So we're going to represent these finite state machines with this state diagram. And with the state diagram, you can create the state table. And you can go the other way too. You can create the state diagram if you're given a state table. So here's the 3-bit counter, which is just one more bit, but now we can count up to 0 through 7. So again, we're going to start with the state diagram. We go from 0 to 1 to 2, 3, 4, 5, 6, 7, and do this loop. That's our simple state diagram. We don't have any indication on the transitions, which just means that we're always transitioning. There is no inputs. And then we have the state encoding for the state inside the circles. So this is state 0, 1, 2, 3. And then from the diagram, we can create the state table. So here, if we're in state 0, the next state is state 1, which is shown here. If I'm in state 0, I always transition to state 1. Okay. If I'm in state 1, I'm going to transition to state 2, and I'm going to keep doing that until I'm in state 7. I transition back to state 0. So this table is the same thing as this diagram. Right? And then the excitation table will be the same table, but if we had any inputs, they would also be here. And it would show basically based on the present state and the inputs, what is the next state and the outputs. The state table would normally also have the inputs, but it would only show next state. It wouldn't show output. So the excitation table is just the same state table, but now you also know what the output is. And then from the excitation table, like we just saw with the other example, we can create our truth tables. With the truth table, we can create our K-maps. We can create the combinational logic circuits to implement that finite state machine. All right, so there are two different kinds of finite state machines that we are covering. That is not what I wanted. We have Mealy or we have Moore machines. So a Mealy machine, the main difference is the output Y is going to depend on the current state X as well. I mean, the current state S as well as the current input X. So that's how you get something like this, right? You have the current state coming out of the flip-flop, goes into this combinational logic block, but also the current inputs. That gives you the output Y. But for a Moore machine, the output Y only depends on the current state. So that's why you have this diagram. You have the current state going into the combinational logic. Nothing else goes in. There's no input from the current inputs into this combinational logic block to figure out what the output is. And then the main differences between their state diagrams. On the Mealy machine, you have the inputs to trigger the transition, and you have this slash, as well as the outputs. So it's inputs and the outputs. Because again, our output depends not just on the current state, but what is the input. So if I'm in state 0, if I get an input 1, I'm going to S1, and my output is 0. If I'm in state S0 and the input is 0, the output is still 0 though. But then if we go over here, where we'll find the outputs for the Moore machine is in the state itself. So if I'm in state 0, output is 0, always. If I'm in state 1, output is 0. If I'm in state 2, output is 0. State 3, output is 0. State 4, output is 1. So we can see that it only depends on the current state. And then what goes on the transition is just what is the input that triggers that transition. So if I'm in state 0, if I get a 1, I go to state 1. If I get a 0, I stay in state 0. So those are Mealy and Moore machines. Yes. I will go over exactly what this one is doing, but you're gonna guess first. So the Mars rover has a binary input X, and when it receives the input sequence 0, 0, 1, so when input is 0, and then the input is 0, and then the input is 1, that means that its sensor has detected life on Mars. So in that case, it wants to output 1 to send a signal back to us that it found life on Mars with that sensor. So the pattern recognizer should have what? And that is your question. If I want to recognize 0, 0, 1, how can I do that with finite state machines? And this one is more just asking how many states do we need? And again, just use the same question, just change your answer. Okay, I don't see anyone changing their answer anymore. Is anyone still thinking about it? All right, so do talk to each other. We don't have many people choosing the right one yet. So maybe if you discuss and talk about it, it might trigger something. The key as a hint is, what do I need to remember, right? Okay, so I again hear discussion diverging now. We did have quite a lot of movement towards the right answer. So what do we need to remember for this? We need to remember that we saw a 0, and then another 0, and then a 1. So there's multiple things that I need to remember. If I have one state, what can I remember? 1 bit, right? So one state is not good enough, right? I would only be able to remember if the previous one was a 0 or a 1. I would not be able to remember that there was a 0 and a 0 and then a 1. What about 2 states? I could remember 0 and a 0, right? But again, I need to know that there was a 1. So 2 states is not enough. So we need more than 2 states. And nope, not highlighter. So we need more than 2 states because we need to remember the sequence of 3 binary inputs. And with 2 states, we can only remember 2. Oh, I circled the wrong thing. So we need more than 2 states. So now that we know that we need more than 2 states, for that Mars rover, we need to recognize 0, 0, 1. Which one of these, or none of them, implements a Mealy finite state machine that recognizes 0, 0, 1, as in it outputs 1 when the input sees this pattern 0, 0, 1. So again, work on this on your own at first. Okay, so I don't see answers changing as much. We are very close to the threshold, but we're not quite there. So do talk again to the people around you. Talk about how you got to your answer. Walk through the finite state machines together, and see if you are convinced to change your answer. All right, I don't hear discussion anymore. do change your answer if you were convinced to change. Okay, we did have a little bit. All right. So we want to recognize the pattern 0, 0, 1. So let's think about in these finite state machines, what is each state remembering? Okay. So if I'm in state 0, I ended up in state 0, either it's always because I saw a 1, right? So like from myself, if I see a 1, I stay, right? If I was in state 2, I see a 1, I come to S0. If I'm in state 1, I see a 1, I come to S0. So no matter where I came from, if I'm in S0, that means the previous bit I saw was a 1. So really, you can think of S0 as I've seen no 0 yet. Okay? So there's 0 zeros so far. But if I go from S0 to S1, I'm in no zeros, right? But I transition to S1 when I see 1 0. But output is still 0 because I've only seen 1 0, right? So S1 means I've seen 1 0. And then if I see a 1, that's why I go back to S0, because now I have to restart, because now I'm not seeing the pattern 0, 0, 1. I saw a 1 now. So now I need to go, and I've seen 0 zeros in terms of this pattern. But if I see another 0 from S1, I go to S2. So S1, I've seen 1 0. If I see another 0, then I go to S2. S2 means I've seen 2 zeros. Or we can say at least 2 zeros, because if I see a 0, I stay in S2, right? So at least 2 zeros is S2. And then if I'm in S2 and I see a 1, I've seen 2 zeros, and now my input is 1. That's why my output is 1. So this one, A, works for this 0, 0, 1 pattern recognition. See, so the second one, S0 is still 0 zeros, S1 is 1 0, but then it's recognizing on 1 0 1. So it's not doing it correctly. So that's why we don't like B. All right. So let's go through this one together. The question is, what does the state table need to show to design the controls of C1? So we can just look at C1. What's my input? I have 2 inputs, right? I have the current inputs, and then I do have the current state. And then what is C1 connected to? It's connected to the flip-flop, which is storing the state. So the input to the flip-flop is the next state, right? So this is current inputs, current states, and my output is next state. So we like A. Current input, current states. If it's not current output, that is the job of C2. Right? So we don't like B. Current input, current states, current output, next states. Again, we're not handling the current outputs in C1. So we've confirmed that we like A, right? So how to go about making this combinational logic and circuit implementation of the Mealy machine. We have the state diagram that we can create just from the description of the problem, right? So we had the description of we needed to recognize 0, 0, 1. And we can create this finite state machine diagram. And then we give our states their assignments. So if I'm in state 0, if my input is 0, I go to state 1 and my output is still 0, right? If I'm in state 0, I get input of 1, I go to state 0. Right? And we saw that if we ever get an input of 1, we always go to state 0. It's just if we're in state 2, that means we've solved 2 zeros already, so that's why we're outputting 1. So we can see that this state table is the same thing as this, right? And then once we have the state table, we need to give our states the binary values that they will actually be represented by. And like I mentioned, the convention is S0 is going to be 0, 0. That's why we see this. So wherever it was S0 in the table, it turns into 0, 0. It was S1, it's 1, right? So this is S1, this is S1. And then 2, 2, 2. And then we don't have a third state, so the encoding 1, 1 is just not used in this case. Well, I mean a fourth state, right? But we're not using 1, 1 to represent S3 because we don't have an S3, right? So then from these tables, we can create the excitation table, which is going to have our state bits. This is the first 2 bits of Q1, Q0, and then the input of X. And then based on those, what is my next state, D, and what is my output? And then like we mentioned, we don't have an S3. So for those combinations, we put don't care. Because we don't care what it outputs. If we get that, it shouldn't come into that state. But we can make our design simpler if we put it as don't care. Because now with the don't cares, it can be treated as a 0 or 1. So we can maybe make larger circles on the K-maps, right? And now that we have this excitation table, we have 3 outputs. That's 1 K-map, right? 3 inputs, 1 output. That's another K-map. That's another K-map. 1 K-map for every output bit, right? So here's our K-map. This one is for, what is this one for? So 0, this is for D1. What would we circle here? We can circle this and this, right? So that's why we have 2 implicants. And then for D0, we would just circle that, right? It's the only case where it's 1. That's how we just have 1 implicant. And then the same thing for Y. Right? So that's how we can get our 3 equations. And once we have our 3 equations, we can draw all the circuits, right? This is for D1, that we found. This was the equation for D0. This was the equation for Y. And what's just not shown here is that we have to do this, right? And in order to make, that's not connected to the right thing. In order to make it not, we would do that, right? But again, you don't need to show that if you're showing this is labeled here, this is labeled here. We know that's the same thing. But that is our process. Make the finite state machine diagram, create the state table, give your states their binary encodings. Once you have the state table, you can create the excitation table. And once you have the excitation table, you can create your K-maps. And with the K-maps, we can create the combinational logic that we need. Right? So that's how we're going to make these finite state machines. All right. So we were asking about the Moore machine. So what if we wanted to do the same thing with the 001 pattern detection, but we wanted to use a Moore machine? Is the question. Which of the following state diagrams implements the correct Moore solution? So we don't have too much time, so just do this on your, like, together first.
Looks like a neural network.
Doesn't look like.
I mean, it's not like side example, very basic like that.
Okay. So going over this together. Does this one work? Yes, it works, but it's the Mealy implementation, right? We want the Moore solution. So we can immediately cross it out just because it has these transitions with the outputs, and there's no output in the state, right? So it's a Mealy implementation. This one is a Moore implementation, so we just need to check it. So S0, my output 0. If I see 1, 0, I go to S1. So S1 means I've seen 1, 0. If I see another 0, I go to S2. S2 means I've seen 2 zeros. And then if I see a 1, I go to S3. So S3 means I've seen 0, 0, 1. And then we can just check that the other transitions are right. So F0, if I see a 1, that means I'm back to seeing 0, zeros, right? So that's why I stay. If I'm in S1, that means I've seen 1, 0, but if I see a 1, I go back to S0. And then if I'm in S2, I'll stay in S2 if I see a 0, because that means I still have seen at least 2 zeros. If I see a third 0, that's still fine. I'm looking for 0, 0, 1. And then if I see a 1, I go to S3, and that's our pattern 0, 0, 1. But if I'm in S3 and I see a 0, I go to S1, because that means I've seen 1, 0, right? And then I'll go to S0 if I see another 1, because that means I've seen 0, 0. Okay, so we like B. So this goes back to your question from earlier of what are these things? And they're not the exact same implementation, but this is just like a example of a finite state machine diagram. And the 1 is just in the final state because that's what the design would have specified as well. So just like that one, we have a 1 here because this is when we reach what the output should be, when it should be 1. If S2 sees a 1, it goes to S3. So we'll finish these slides on Wednesday, and we'll also go over the lab on Wednesday. You're doing registers and counters. So